All right. Hello, everybody. Welcome back to Archaeology with Flint Dibble. Let's just do a quick sound check. Sam, do you mind saying hello?
Hello, Flint. Are my audio levels appropriate? Am I coming through okay?
Yeah, they are for me. So there's always a lag between when we do stuff and what the audience hears. So if the audience could chime in and tell us when you're ready that you can hear us. In the meantime, I think I'll just kind of start a little bit. We're here to talk about radiocarbon. Dr. Sam Gregson here. He's with the YouTube channel Bad Boy of Science. And so the idea is we're gonna rock this out. We're gonna talk about physics and archaeology, do a little bit of collaboration, because I think one of our big goals is we want to represent scholarship and scholars and educators on YouTube. We've already done some collaboration. We're hoping doing this now, and we're hoping to do some more in the future with us and everybody. It sounds like the sound is going well.
Good.
So perfect. So we're going to talk about the physics of radiocarbon of C14. It's a really important topic. Just a quick disclaimer, neither of us are experts on C14, but we understand it from different perspectives. It's something that we come across the basic concepts of in what we do professionally and in our education, and so we'll walk through some of it and why it's so important and why it's really cool. I always have to throw in this slide whenever I teach about dating, archaeological dating, because like
Is
you
this
gotta
is this
have some
something
fun.
is this something that was on a website here, Flint? Maybe for a left or right swipe here? Was this has this seen
Yeah,
has
exactly.
this seen action? This is the
This is
question.
in action. No, this is that
Right.
classic meme. And when I
Okay.
was teaching a class on archaeological chronologies, I was like, you got to have some fun. I have some more dating memes in there too with
Good.
archaeology
Good.
because
Excellent.
it's such a good source of humor.
Good.
So the idea is really how old is something, right?
Mm.
That's not so easy when you're doing archaeology. You dig up something, you come across a monument, and it's like, how old is this thing? And that's so important because if you want to answer questions of history and prehistory, you need to know what comes first, what comes second, what comes third, and how they all line up with other sites and other monuments and other artifacts and other cultures. And so it's really not so easy. And we're going to walk through also the history of this from the 19th century onwards and why it's not so easy as well and why it matters so much.
Mm.
And so, I'm here joined by Dr. Sam Gregson. He is on YouTube at the Bad Boy of Science. He is a professional science communicator. He does public lectures all the time. He does a lot of YouTubing. He does a lot of other things. And you should go check out this video that we did on his channel, I don't know, a while ago at this point, several months ago. And it was about ancient technology meets modern technology and detecting dark matter using archaeological artifacts, so
Yeah.
really old Roman lead. And that was our first time chatting like that, and I think we want to do a lot more collaboration. So Sam, do you mind just introducing yourself to everybody as well?
Yeah, for sure. So first of all, thank you very much for having me, Flint. It's been amazing to watch your rise since we last chatted. Um, because you're an extremely entertaining guy, putting out amazing things, and also because of the message you're getting out there. So I'm really glad to see your rise and also to be back to discuss this because, as you said, there's a lot of interaction, although many people wouldn't think of it in the first instance, between particle physics and archaeology. So we have people using muons to look for chambers in Egyptian pyramids. We have people using ancient lead from shipwrecks, Roman shipwrecks, to look for dark matter. And today we're going to be using or talking about nuclear dating. So there's lots and lots of overlap, although people might not have thought, between the subjects. Now, my name is Dr. Sam Gregson. My background is I was a particle physicist at the University of Cambridge, and I worked at the Large Hadron Collider in Geneva in Switzerland, the world's largest atom smasher, essentially. And now I do a hell of a lot of outreach. I have a YouTube channel, Bad Boy of Science, and I try to explain particle physics and other science in a kind of fun and accessible way for lay people. So it's a great pleasure to be back, and I'm excited to do the second in this kind of mini series of overlap between archaeology and high energy particle physics.
Yeah, and that's our goal. We've been chatting about collaborating for, I think, like a year now, and almost at least. And so it's been something that's been on our radar, and it's like, how can we share how physics and archaeology relate? And to be honest, from the point of view of archaeology, this is the big one. You know,
Yeah.
like from the point of view of particle physics and atom smashing, the one we did on your channel, where you use ancient lead and stuff like that from Roman shipwrecks to actually build a particle collider,
Particle detectors for
particle
dark matter.
detector.
That's right.
Yeah, so that's big news for physics. This
Yeah.
one now we're thinking this is really, really big news for archaeology, and so we're thinking about how we can apply physics to that. And a little preview ahead, there's a Nobel Prize involved, one of only 2 Nobel Prizes in archaeology topics.
The interesting thing I found, Flint, as well, when I was researching more for this discussion with you today, is I hadn't realized just how many subjects carbon-14 has an impact
Yes.
in. So we're probably going to cover climate today, thinking about the sun, thinking about dating in archaeology. Lots and lots and lots of fields have made progress because of carbon-14 and carbon-14 dating. So many people have described it as kind of an atomic bomb in archaeology. And other people have said that it's very, very rare that such a discovery in chemistry has such a massive impact in so many fields. I hadn't realized just how impactful carbon-14 is. So I'm really excited to tell people with you a few more things that it's involved with that they might not be aware of.
Yeah, 100%. Thank you for the super thanks, Howie. I really appreciate it. And yeah, I completely agree. It really is that atomic bomb, and we'll certainly get through that why. I do want to start off by Lord Colin Renfrew, one of the most prominent archaeologists of the second half of the 20th century. We'll actually discuss some of his research today. He just passed away, I think a week ago today or a week ago tomorrow. And he's really one of the major innovators in the field of archaeological thought. And back in the 1970s and 1960s, he was one of the major innovators in applying new archaeological chronologies from radiocarbon dates to the field. He's the one that coined the term, I think. He certainly has a book with it titled The Radiocarbon Revolution, Before Civilization. It's right here, The Radiocarbon Revolution. And so, you know, he was one of the major innovators in trying to think through new chronologies. And I had the privilege of meeting him a few times, and I've heard so many stories about his dancing abilities at conferences. He was a very prolific, folk dancer whenever he went to an archaeological conference. And he was a very, very nice dude as well, and very generous with, must be thousands upon thousands, maybe tens of thousands of archaeological students over many, many decades. And so he absolutely revolutionized the field. So a quick moment of silence for Colin Renfrew, and he is missed. Okay, so Sam, start us off. Tell us how this all starts with the sun.
So I have to pick you up on a minor thing straight away, Flint. So
Yeah.
I know people are watching your channel to try and pick you up on minor mistakes. This is a well-known thing at the moment. So it does start with the sun to some extent, but also with the wider galaxy as well. So it starts with what we call cosmic rays. These are subatomic particles that continuously rain down upon the Earth from all directions. So we're talking about mostly galactic cosmic rays. These come from things like supernovae explosions, also some from the sun. They're largely protons and atomic nuclei. These are high energy particles that are streaming through our cosmos, and they smash into the Earth's upper atmosphere, so the troposphere and the stratosphere, and they produce thermal neutrons. And these thermal neutrons interact with nitrogen in the upper atmosphere, nitrogen-14.
Okay.
And the nitrogen-14 captures one of these neutrons, knocks out a proton, and turns it into carbon-14. So these cosmic rays coming from deep outer space are producing carbon-14 in the upper atmosphere. Now, carbon-14 is a radioactive isotope of carbon. So most carbon is carbon-12 or carbon-13, but we're producing this radioactive version, carbon-14, in the upper atmosphere. And the highest production rate is about 10 to 13 miles above the Earth's poles, where the magnetic field is strongest. And this.
So, quick question. So it's not
please.
the sun that's actually doing this. It's actually cosmic radiation from the birth of the galaxy, in a sense.
Well, not necessarily
both.
from the birth of the galaxy, but from explosions of stars and from being sped up by kind of cosmic phenomena as well. But it's both. also
Okay.
some with the sun. Just to say, I don't want anyone to jump on you when you say it all starts.
Look, anyone who's going to jump on me for making a mistake about
anyway.
physics,
Yes, okay,
which
fine.
they friggin' will, is a loser, okay? So I don't really care. Like,
So this carbon-14 gets produced in the upper atmosphere, and it stays roughly the same level throughout time, roughly, because we are going to come back to that. So it decays away because it's radioactive, but it's also being replenished all the time by these cosmic rays.
so
Now
okay,
this-
I have a quick
Yeah, please.
question. So, this is actually something I learned today when I was looking through your notes and stuff like that. I didn't realize that the element itself changed, right? From nitrogen to carbon, and then with radioactive decay from carbon to nitrogen. And so, does that happen often in nature? Is this like a super uncommon, or is it a common thing with different elements? Like, what's up with this?
No, so we can get common changes like this in beta minus and beta plus decay that we call it. So the nature of the element, the whether it's nitrogen, whether it's carbon, whether it's something else, is controlled by the number of protons in the nucleus. We call it the atomic number. So if you lose a proton, or you gain a proton, or a neutron is changed to a proton, or a proton is changed to a neutron, then you change the nature of the element. You change the number of protons in the nucleus there. So this is something that happens fairly commonly.
Yeah, see, I just assumed it was the neutron that was changing, and it was reverting from carbon-14 to 13 or 12, a more stable version, which I study in teeth. And so, yeah, this is something new to me. I did not realize that the protons would change like this as well. And so by radioactive, in a sense, what you mean is that with time, the proton just changes naturally back to the number for nitrogen. So it goes from 14 to what, 16 to 13?
Exactly. So it goes from 6 in the carbon 6 protons to
6
7.
To 8.
But the mass doesn't
6
change
to 7,
because the
yes.
proton and the neutron have the same mass. Exactly. So the 14 stays the same.
It's both, yeah.
But the 6 changes to a 7. So we create this carbon-14, and then over time it decays away back to the nitrogen over time. So this is being produced in the upper atmosphere, and you might ask, well, how is that related to archaeology? Why should I care? Well, this carbon-14 reacts with oxygen in the upper atmosphere to produce carbon monoxide and then produce carbon dioxide. So we now have carbon dioxide, which contains this radioactive form of carbon, and that descends down into the atmosphere and diffuses around the world, dissolves in the oceans. And it's also taken up by living organisms. So in photosynthesis, carbon dioxide is taken in by plants, like trees, like plants. Animals eat those plants. So they're all taking up this radioactive form of carbon along with normal carbon-12. So while an organism is alive, they're taking up carbon in the ratio of carbon-12 to carbon-14 that exists in the atmosphere while they're alive. Roughly. This is particularly true on the land. So these creatures are in equilibrium with their environment. They're taking up carbon-14 at essentially the concentration which is in the atmosphere at the time. Now, of course, when they die, they stop taking carbon into their body. So the living processes stop. They stop taking carbon into their body. And essentially now we start a clock. The carbon-14 that they have taken up starts to decay at a very well-known rate. This is a half-life of about 5,700 years. So half of it disappears almost every 6,000 years. So if you can now take a measurement of the amount of carbon-14 in something today, and you can then project that back and work out how old that thing must have been, because you know the rate at which this carbon-14 decays. So we take a measurement today, we see how much carbon-14 is in our piece of bone that we've dug up out of the ground, and we say, okay, that's the ratio between carbon-12 and carbon-14 today. I know how quickly carbon-14 decays. I can project backwards, and I can work out roughly the age that
And what you're doing is you're actually analyzing the ratio of these isotopes of carbon-14 to carbon-12, which is a stable isotope and does not decay. And so, this kind of phenomenon is started with carbon-14 for archaeology, but we actually do it with a number of different isotopes now, not to understand age, but it's the same idea when an animal or a plant or a human form, in a sense. They eat, they drink, they photosynthesize, whatever the heck they do is the kind of organism they are. They lock in that signature from the geology, from the water table, from the atmosphere, into their own tissue. And so when a lot of our tissue, for example, so look, I'm an environmental archaeologist, I study animal remains, and so, for example, our teeth, they actually are fairly static from once they grow, they're inert and they don't change over the course of your life. On the other hand, your bones are constantly remodeling and changing, so it's actually getting the signature around the time of your death, not the signature at the time of your birth. While your teeth, on the other hand, would have more of the signature at the time of when the teeth are growing, rather than the time of your death. And so it locks it into the matter, that organic material that then preserves in the archaeological record. And then with the C14 decaying at a known rate, we can then predict that ratio of C12 to 14 backwards. So
and it's interesting what you say, because it's very important to know what type of material you're dating, because there can be a number of complications. So you obviously need organic material.
Oh wait, we're going to get to that. We're going to get
all
to
right,
that.
okay.
Yeah, let's wait on that. Let's not get into problems yet. We're just introducing the concept now. Now let's think for a second about archaeology. So how do you actually date stuff? You know, before there was radiocarbon, you're sort of relying on historical dates if you want to get an absolute date. So like, you know, the Pantheon in Rome, fortunately, written right on it, it says Marcus Agrippa, when he was the consul for the third time, he built this. So we know from our historical sources when Marcus Agrippa was consul for the third time, and boom, we can date that. Just like a coin in your pocket, it has a date on it, and we can start to date it, or like scarabs from Egypt and stuff like that. At the same time, maybe we have things that don't have an exact date on it, but we know that material culture, artifacts, their style changes over time, and we can start to put that in order, just like we can with models of cars, right? Maybe you don't know which date a certain car was built, but you can see the progression over time in a junkyard, and you can start to get a sense of that. And that's called, you know, stylistic, and we can combine that with stratigraphy, the relative layers that are deposited at an archaeological site, to put that stuff in order, the sort of stylistic changes over time. And this gives us what's called relative chronology, the order of a sequence of things. And this is really useful, and it's what archaeology was, what a lot of what our work actually is developing these relative chronologies with architectural styles, ceramic styles, whatever, stone tool styles. That's what we do. But what it doesn't do is it doesn't give us an absolute date. And so early on, what we relied on is those few cultures that we have historical records that go back thousands of years, like ancient Egypt, right? We have these king lists that tell us about, you know, this king after this king after this king after this king, and these pharaohs really, and we can approximate how long pharaohs would rule for, and then we have material culture like scarabs that are marked with this, and then they get traded to places like Crete or Greece or whatever, and that helps us lock in these kind of artifact dates, right? And so that's what archaeologists did through the 19th century, through the first half of the 20th century, and they developed, in a sense, what's called culture history. This is this phase of archaeology that existed at that time. It was this sort of historical putting together of cultures. But since it's based off the trade of these materials from historical societies with historical dates like Egypt or Greece or whatever, it biases our interpretation. And so for a long time, archaeologists believed that society sort of developed in the sort of southeast in the Mediterranean, and it diffused, it was traded up further to the west and to the north. And this impacted the chronologies of everything, of when we dated stuff. And so this is kind of Gordon Childe. He was the last great cultural historian. He really kind of defined that concept and put together these really complicated chronologies of this kind of pottery relates to this kind of pottery all over prehistoric Europe, and put together these kind of history of cultures. And this is where things stood kind of up until World War II and the development of sort of atomic, you know, physics and things like that, that sort of ushered in this new method that helped us check what was going on. And so the only checks we had before were kind of occasional environmental sources, like counting back tree rings or varves, which are sort of year by year new sedimentary layers get developed, and if there's an artifact in there, we can get a sort of absolute date. And so this is where we hit you and the discovery of radiocarbon dating. Tell us a little bit about Willard Libby in this story.
Yeah, this is a really amazing story. It was really fun to kind of dig into this history. So as you said, in the middle of the 20th century, archaeologists didn't have many ways to kind of do these absolute dating. So maybe you had to rely on a direct text record, or you had to link to, you know, an eclipse that happened or something like that. But these are not common events. So
Which, by the way, that's a useful point. Using that kind of archaeoastronomy, the kind of records of an eclipse, is how many of those Egyptian king lists got locked into place.
okay.
So, you know, like if they mentioned that during the third rule of some pharaoh there's an eclipse,
Yeah.
astronomers would time out when that eclipse could be, and then they can start locking in those king lists with what are called fixed dates, fixed points. And so that's how relative chronologies are kind of built, is on these kind of fixed points, right?
Amazing
Yeah.
stuff. So in the in 1940 there were two scientists called Martin Karman and Sam Rubin, and they were working at the radiation lab in Berkeley, and they were testing organic matter to try and find isotopes with half lives long enough to be used in biomedical research. So they ended up synthesizing C14 using an accelerator, and what they noticed that it had an incredibly long half-life, and this would become useful for dating over a long period later. They didn't really peg that to dating at the time. And then a chemist called Serge Korff came along and predicted that we could produce carbon-14 by the methods that I talked about with cosmic rays and thermal neutrons in the upper atmosphere. He was working at the Franklin Institute in Philadelphia. Now, these people were putting this work together, and at the same time, a chemist who was initially at the University of California, Berkeley, before the war, called Willard Libby, he heard about this work. He heard about this idea of carbon-14 and the idea that it could be created in the atmosphere. And he wondered if you could use it for radiocarbon dating. Now, at the time, he couldn't work on this straight away because he was actually working for the Manhattan Project's substitute alloy materials laboratories at Columbia University. So he was, during the war, an actual Manhattan project scientist working on the bomb, working on gaseous diffusion processes for enriching uranium for the bomb. So he had this idea of radiocarbon, but he kind of had to sit on it for a little bit because he had a kind of more pressing engagement to deal with, shall we say. Now, when the war ended, he moved to the University of Chicago in 1945, and he started working on the idea of potentially using radiocarbon for dating. So there's a famous paper in Physical Review in 1946, where he proposed that you would be able to find this carbon-14 in living organisms. They found it in living organisms. It was been taken up by living organisms. And he further developed this idea with some collaborators in science in 1947 and 49. And what they did to prove that they could kind of make this work was they took methane from sewage works and showed that it contained carbon-14. So this is modern methane that has come from, you know, people having a poop and it going into the sewage works. This contains carbon-14 because there's carbon-14 in the atmosphere. And they also took petroleum, which is obviously derived from fossil fuels, and showed that this petroleum had no carbon-14 in. So this was the first kind of qualitative test of carbon-14 dating. Really old carbon, petroleum, has no carbon-14 in it because it's all decayed away. But this new stuff does have carbon-14. And people are taking in carbon-14 from the atmosphere, and when they go to the loo, they're flushing it away. So this was the first kind of idea, or the first demonstration, qualitative demonstration in 46 and 49, that they could do this. Now, while they were doing this, one of Libby's first graduate students, called Ernest Anderson, he established that organic materials and organisms at different latitudes around the world essentially took up radiocarbon at about the same concentrations. So this gave the idea to Libby that maybe we could use this around the world. Maybe, although this stuff is being produced in the atmosphere and more at the poles, it does diffuse around the world, and therefore we can use it all over the world. And now we get to the famous kind of paper that you clicked on with the nice graph. Yeah, exactly.
Yeah.
So to do the actual quantitative demonstration that this carbon-14 dating worked, what Libby did was he worked with some of his colleagues, including anthropologists like Robert Braidwood at the University of Chicago's previously called Oriental Institute. I think that's probably a little bit not PC nowadays, but now known as the Institute for the Study of Ancient Cultures. And what they did is they took a load of artifacts from the museum's collections where they had a known chronology. So they had a known antiquity, they had a known date, and they tested them with radiocarbon dating. So they took a rope sandal from a cave in Oregon. They took some dung from an extinct ground sloth. They took linen wrappings from Dead Sea Scrolls. They took part of a funeral ship from Sesostris III of Egypt. You'll probably know that name far better than I do. And even a piece of charred bread from the ashes of Pompeii. And 2 samples from the tombs of 2 Egyptian kings. I'm going to butcher these names, Flint. Zoser and Sneferu.
Yeah,
And
that's good enough. Joseph, but yeah.
Okay, good. I didn't butcher it too hard. And essentially what they did was made this beautiful graph, which Flint is showing here. They took radiocarbon measurements from these samples, from the artifacts that were in the museum of known antiquity, and they predicted the age of those objects using radiocarbon dating by measuring the amount of radiocarbon that was in them at that time in about 1950 and projecting backwards to see if they could predict the correct ages of these materials of known age. And you see here that they did a very, very beautiful job. So they produced this graph here, and all of the points are the measurements with error bars, because obviously you can't get a perfect measurement, and the line of the true ages, so that we get a very, very beautiful fit between the predicted ages and the true ages.
So one thing I want to really emphasize to everybody who's listening is the importance of multiple lines of evidence here, right? It's not. This is, in a sense, a technique developed from physics, theoretical physics to practical physics, and then it's tested against a whole range of different things. So you can see it's tested against like redwood trees, where we can count those rings back. So environmental sources, it tests our understanding not only of C14, but of dendrochronology, as it's called. It also, we're talking about those dates we talked about before, those historical dates and how they locked in Egyptian king lists and things like that. It's actually testing that at the same time as well. And it's showing that things like Sesostris and other Egyptian sort of sites that we assumed we understood the date from because of the historical chronology that archaeologists had developed in the previous 100+ years. And boom, it matched out pretty well. Same thing with things like Roman chronology in Pompeii, as well as chronologies in the Americas. And so it's showing all these independent lines of evidence coming together and matching, showing that this method is very, very effective, but so are many of these other methods. It's sort of independent confirmation of each of them. And so that's actually really cool to be able to see that. And I think this idea of multiple lines of evidence, it's something that I'll want to talk about later as we keep going.
Yeah, it's really, really cool because you could imagine, exactly as you said, we've got some tree ring dates in there from a redwood, for example, but you could imagine if one of these dating methods that you've talked about was wrong, one of these points would be far away from that line, and we simply don't see that. We see that this lining up pretty well, and so this was basically the start of radiocarbon dating, and it works pretty well, despite the fact that in the 1950s when they were doing this, Libby was making a bunch of assumptions. So they were assuming, for example, that the level of carbon-14 in the atmosphere over many, many years, over thousands of years, is the same, which is not exactly true. We're going to come on to that later. Also, they had the half-life, so the rate of decay of carbon-14, a little bit wrong. So we now have a half-life of 5,730 years. He was using 5,720, and then actually went the wrong way with a new measurement that went the wrong way, which went down to 5,570. So despite these flaws in this methodology, they were making really good progress and seeing that this method essentially worked. There were things that needed to be ironed out, but this really showed that this methodology could work. And this is essentially where, as you flagged up earlier, the radiocarbon revolution began.
Yeah, exactly.
So after this, the news spread very, very rapidly. So by 1960, there were more than 30 radiocarbon labs around the world. And as you mentioned earlier as well, Libby received the Nobel Prize in 1960 for this work. So it was a nice cap off of working on the Manhattan Project and then 15 years working on this project before he received the Nobel Prize in 1960.
Yeah. And so from an archaeological perspective, this really revolutionized everything. Now we had this independent confirmation that we could use all over the world, right? It was available for use fairly quickly in the 1950s and in the 60s and 70s. It obviously took getting a large number of samples to really start to understand what it meant. But at the same time, once we started getting those samples, it turns out that while certain things archaeologists were right on, we talked about the pyramids in Pompeii and stuff like that, but other things they were extremely wrong on. And a lot of that had to do with that trade on down the line, that kind of diffusion model that was seen before ex oriente lux, so light from the Orient, everything comes from the east, goes west to north in sort of the European context. That turned out to be somewhat wrong with certain things. So one of the big things it was wrong on was megalithic tombs. For 50, 100 years from the first development of archaeological chronologies in detail by Oscar Montelius, and he's from like the Nordic countries, to Gordon Childe, there was this idea that megalithic tombs started out in Greece with the development of Tholos tombs, and they moved west and north up until they hit, the UK. And once we started taking radiocarbon dates from these tombs, it turns out that chronology was all wrong. It was completely wrong. In fact, the earliest megalithic tombs existed in Northwest Europe. They were built there before the Tholos tombs in Greece.
Have we got a win here in the UK? Were we the first on this?
No, I think it was in northern France. It was the first ones. That's what this map from Renfrew shows. And so, but what this meant is we have to stop thinking about archaeological change. So for 100 years, so many archaeologists thought of cultural changes over time from one society to another as a result of migration or diffusion. So the movement of people or the movement of ideas and goods and how to build stuff and stylistic things. And so now we had to realize, oh no, stuff doesn't always diffuse. Not everything comes from Egypt and Greece, right? It turns out that sometimes locals in different areas of the world develop things independently of one another. And so now far more local explanations are needed. And Colin Renfrew, who I mentioned, he was one of the big ones that argued this for megaliths, and others in the 60s and 70s and 80s started making these arguments all over the world. And that's another important part, is the global nature of this. For a
I was going to say, this is where they come in with the aliens, right?
Yeah, exactly.
The aliens taught them all over the world.
In the 19th century, many people believed that, these developments of ideas like pyramids, they start off in Egypt and then they diffuse out across the world. And that's what hyperdiffusion is an idea spreading across oceans. And so the idea is this thing looks like that thing looks like that thing. And therefore they all have the same origin that they diffused from. And people make this argument with pyramids, they make this argument with friggin' swastikas, for fuck's sake. And so now that we actually have radiocarbon dates, we actually understand that pyramids in one place, they don't date in that way. The chronology of it doesn't make sense. Same thing with objects with swastikas, same thing for depictions of handbags or whatever the heck it is. They don't all have a common origin. In fact, we know from radiocarbon dates, from the layers that they are in, that they clearly developed locally, independently of one another. And so
very interesting to see this almost convergent evolution of cultures, right? Lots of people coming to the kind of same solution for things, whether that be, burying the dead or building a particular monument to a king or whatever it might be. They seem to come up with similar solutions in different places. That's very, very interesting.
Yeah, which I think makes a lot of sense. I like to use the analogy of convergent evolution. I think it's a good analogy, though there's also, that takes too long, but there's also issues with it. But I think the key thing to remember is that people are smart. And so, of course, people come up with parallel ideas and ways of solving similar problems, just like we do today in our own tech world. We hear about two people coming up with the same idea at the same time. The war between Bill Gates and Steve Jobs, or whatever it is. And so to get a sense, I think I saw somebody in the chat ask earlier about how do we date something that doesn't have organic material. So I did want to use the example of Gunung Padang, because that's been something with this kind of pseudo-archaeology. And yeah, you can't do radiocarbon on the stone. But what you can do is you can understand the stratigraphy. And so you can take radiocarbon samples from underneath walls. And if you get dates from underneath those walls, you know that that organic material dates to before that wall was built.
Yeah.
That's why we know that that retracted paper that dates Gunung Padang to like 20,000 years ago, it's a bunch of bollocks. It says, oh, let's dig a core 20 meters down, so 60 feet down, and take the oldest carbon and therefore say that that dates the monument. Nuh-uh. How about we take a piece of carbon directly underneath that wall? Right? Because the carbon directly underneath that wall also predates that wall. So therefore, the date of the monument is only 2,100 years ago, not 20,000 years ago.
So I'm going to push back a tiny amount, Flint,
Yeah.
with just from something that I read, and perhaps it's totally off base. You tell me as an expert in archaeology. So they were saying this kind of relative data, obviously very, very useful, but you have to be a little bit careful. For example, people will take wood that was cut
we're
down
gonna get to
many,
that.
many centuries
Yeah, we're going to
ago.
get to that
Right,
actually
okay,
right
repurpose.
in a next up soon.
Okay.
We're going to get to that exactly. You're
Okay, good. All right. I'm listening and taking it in. Good. This is excellent.
And so at this time, so not only do we have this new method, but it woke up archaeologists. In a sense,
Yeah.
archaeologists all got woke, if you will. And by woke, I mean they realized, hey, we need to be much more interdisciplinary and start thinking about the ability to apply other sciences to the field.
Got to
And
listen
so
to the physicists, Flint. We know this.
not just the physicists, but environmental scholars, geological scholars, even literary and artistic scholars. The point of archaeology is we are such a big tent. Any single discipline out there actually fits within archaeology quite well. And so this is what we call new archaeology. It's also sometimes nicknamed processual archaeology, but that is where archaeology sort of wakes up and sort of says, whoa, we need to start checking everything with multiple lines of evidence, and that means dipping into a lot of different disciplines. So now,
did this
yeah.
free archaeologists up to kind of ask new questions as well? Because I guess you were talking about the horrific amount of work that was done to try and get these relative chronologies. Was there now a kind of almost a freedom, a liberation that, look, we can take these measurements and they will give us these answers, more objective answers, and we don't have to spend so much time trying to get the actual dates of things. We can ask different questions about the relations at these sites. Was
Yes
that a change
and
in archaeology at the same
no.
time?
I don't think it really freed up time because we still have to do that. So as I'll get into, for multiple reasons, we still do all that stylistic seriation.
Okay.
We still have to do that to identify different typologies. Part of the reason is because ceramic is much more abundant. So ceramics and stone tools are far more abundant, and we have surface finds where you can't trust, radiocarbon from the surface, right? And so if we want to do that, we need to still use those traditional methods. So those traditional methods never went away. And also for certain periods, they're far more precise. So when you think about a historical period, when you're thinking about the different reigns of Roman Empire, of the Roman emperors, and you want to understand things on a period, on a chronological specificity of every 5 years maybe, because there's major events happening, we can do that with coins. We can't do that with radiocarbon samples. And so there is advantages to being able to still do the same kind of methods we've always done. That said, it did open it up to let us start asking new questions. You're completely right there, but it didn't give us the luxury of just stopping to do what we used to do.
and just to make that clear for people, you said that there are limits on the accuracy that a radiocarbon age can give you, because obviously you're measuring, and we'll talk about how the measurements are done maybe a little bit later. But if you're measuring an amount of C14 today, there's obviously going to be an error on that measurement that you make, and that's going to translate back to a spread in the age of the object. And if, as Flint says, if that gives you a window of 100 years, but you're interested in something that happened in a couple of years, then radiocarbon isn't going to get it for you, and you need these other lines of evidence still. So it doesn't supersede anything, but it's a new string to the bow, as it were.
And I think that's a perfect point to get into, because I think now we're going to delve into some of the problems and the ways that the fields have moved on to solve some of these problems and are moving towards solving some of them. So I guess the first one is this kind of issue of corrections and the atmosphere itself, right?
Yeah, so this was a huge issue. So this was something that Libby realized even back in the 1955. So to date a sample, you essentially need to know the ratio of carbon 12 or carbon 14 that the sample started with. And that actually changes by a few percent each year. There's different fluxes of cosmic rays, different activity from the sun, different behavior in the geomagnetic field of the Earth. So the amount of radiocarbon that's being produced in the atmosphere actually wiggles up and down by about 3% year on year. And as I say, this is dependent on lots of things. So it's very hard to correct for. So actually, since the 1960s, instead of measuring the radiocarbon that we see now and trying to project back, we've actually taken a little bit of a different approach. What we've tried to do, or what scientists have tried to do, is to actually find a sample from every single year going backwards into the past up to about 60,000 years and actually measure the amount of radiocarbon that it has today. So therefore, if you make a measurement today and you get, an answer of 50, you can go to a sample and say, well, what type of sample? How old is the sample that gives a measurement of 50 today? How old is that sample? And then you just get your age straight away. Now, you might ask, how the hell can I get a sample, a historical sample from every single year going back 60,000 years? And the way that we do this, typically, particularly on land, is to use tree rings. So there are trees lay down every single year a new layer of growth. And once that layer of growth is when it's growing, it's taking in carbon 14 at the concentration that is in the atmosphere at that time. When the year ends, a new layer starts to grow, and the older layer is now locked in. It's stuck at that amount of carbon. So it's as if that layer kind of died in terms of carbon 14. It's now starting to decay on the clock. So if you can find these rings going back many, many, many years, and you can test them today, you can work out how much radiocarbon should be in the sample today and how old that ring is, because by counting the number of rings, we can get the age of that sample. So that's what they've been doing over the past kind of several decades, trying to find tree rings that correspond to a year in the past, and then working out how much radiocarbon that gives us today.
Yeah, and just to restate
Please.
for everybody, just because it is a complicated topic,
Yeah.
and it takes sometimes a couple times to wrap your brain around it.
For sure.
So in a sense, the amount, the ratio of carbon 14 in the atmosphere is different every year because of all these different factors from the sun and whatnot, and therefore our dating backwards is going to be off because of that change in atmosphere.
You don't know your starting point.
Exactly. You have to know your starting point. So the best way to do that is with something like tree rings, where you can take, on this one tree trunk, you can start taking a sample at each of those tree rings. Yeah. And since you know when it started and where it ended because of the number of tree rings and counting backwards to what year each of those relates to, you can therefore predict and understand the atmosphere back in those times, and then use that understanding of the atmosphere and the ratio of radiocarbon to correct all your other radiocarbon dates, to calibrate them is really the right term. Yeah,
exactly right. And people might ask, well, how many years can you go back with tree rings? So we have some very, very old trees. I think you had a picture of the bristlecone pines there. So you can get these bristlecone pines that go back kind of 500 years or a couple of thousand years. So you can get samples like that. But radiocarbon dating goes back about 60,000 years. So how do we do that? Well, this is a really amazing thing. So you can take a dead tree, and what we know from looking at trees is that the width of the rings each year has a particular thickness, which is based on how good the growing season was that year, what the temperature was, how much rain there was that year. So you can take a dead tree, and if the dead tree was alive and overlapped with the modern tree, there should be a set of tree rings which are the similar width with one another in that overlapping region.
In a sense, you wiggle them together. You wiggle them together.
Yeah. So a tree that lived, 500 years back into the past, and one that lived from 450 to 950, for example, they overlap by 50 years. And you can match up their patterns of tree rings in that 50 years and work out, therefore, in the dead tree, what are the years in that tree? And you can go tree, dead tree, dead tree, dead tree, dead tree, dead tree. And you can go back about 14,000 years doing this using bristlecone pines.
It depends where in the world you are. It varies in
It does.
different areas of the world because there's different trees there.
That's
in
right.
the Pacific Northwest, there's these great, huge redwoods that are fantastic.
Yep.
But yeah, so that does vary. But that's exactly how we can start testing this going back. Other types of environmental records too help us. But yeah, that's the general concept of it. And then we get these kind of calibration curves. So if you want to explain these a little.
Yeah, exactly. So once you have a measurement of the radiocarbon from each of these tree rings, that's the blue curve there. And you can see it has some thickness because obviously these are radiocarbon measurements. So they have a certain error that goes with them. So there's a thickness to that blue line. These are the radiocarbon measurements today of tree rings of known ages. And then the red bump there is a measurement that somebody has made of radiocarbon on a new object that's just been dug out of the ground, maybe some collagen from a bone that's been dug up from an archaeological site. So when you're trying to get the age now, it's a very, very simple procedure. All you have to do is overlap your red measurement with a tree ring that has the same amount of radiocarbon nowadays. And therefore they must have similar ages. And this takes into account, gets rid of straight away the changes in the atmosphere, everything like that. You've calibrated them away. So you're looking to overlap this red measurement with the blue curve. Now, this brings its own problems. Flint, did you want to say?
I was just gonna. Well, you can talk about some of the problems first. Bring its own problems, then I'll go on.
Exactly. This brings its own problems because you can see that red measurement has an error on it. It has a thickness because we can't measure the amount of carbon-14 perfectly. And similarly, the blue line measuring the carbon-14 in the tree rings also has a thickness because we can't measure that perfectly either. So you can see that the red and the blue lines overlap over quite a large range. And that means that we can't narrow down the age of our new object to beyond where these gray peaks are. These gray peaks are essentially the overlap between the red measurement and the blue measurements from the tree rings. So you can see that there's a width, there's a thickness to that age measurement, and you get a range of ages. You can't narrow in on 1 year, for example. And it can be a little bit worse than that as well, because depending on how the carbon-14 in the atmosphere changed over time, these overlaps you see, the blue line can nip back upwards and they can overlap in different age ranges. So you see on the left of the gray boxes, there's a little bump on the left, but then there's a big bump on the right. So you can get that this object might be between 1,000 to 800 or 400 to 300 years into the past. And you can get this spread, and it's very, very hard to nail down this spread.
And another point to bring up that's really, really important is because these calibration curves are constantly being updated by studying more things of known dates that are known independently. What that means is you can't always trust older research into archaeology or even environmental stuff. The chronologies are off. So, we talked about those megaliths being completely off. That's why you can't trust any archaeology done before radiocarbon. Before radiocarbon, it's off by thousands of years sometimes, some of those dates. But even the very earliest radiocarbon dates that are published are off by as much as like 600, 800 years, depending on where they line up in the curves. And so, as we keep updating these radiocarbon calibrations, you need to trust only newer publications in a sense, and all of them need to be corrected again through this sort of calibration method. And so this is really important to understand that you can't just go pick up something from 1960, even with radiocarbon dating, and think that that date is good. And there's other reasons too, which we'll get to. There's a lot of problems as well. And one of these is
I guess it's important to tell the people in the audience, but that doesn't make it wrong, quote unquote. It's just that science is an ongoing endeavor, and we're getting better and better with these measurements all the time. So
I guess what's wrong is those numbers is what I meant.
Yeah,
it doesn't mean that what they did in the past was wrong. No, and hopefully they publish the uncalibrated value so that we can then calibrate it with this new calibration curve.
Exactly.
And Oxcal, by the way, right here at the website, it constantly updates. They're in, I forget, I think their fourth or fifth iteration of calibration curves. I could be completely wrong on the number there. But you can just take an uncalibrated date and plug it in, and it'll give you the calibrated range. And so, you know, it's actually pretty cool. And so we as scholars need to make sure we publish things in ways that can be updated by future scholars and as well. Yeah. So let's talk about some plateaus. Why do we get plateaus? They're a big problem for archaeology.
Yeah, so this is a huge problem. So we saw that there's an overlap of date ranges from that previous graph there because of the widths in our measurements. Also, because of the way that the carbon-14 in the atmosphere changes, you can essentially get a situation where an object where you measure its carbon-14 today could be slightly older, but there was more carbon-14 in the atmosphere, or it could be slightly younger and there was less carbon-14 in the atmosphere when it was alive. And it's hard to separate out between these two ideas if the carbon-14 in the atmosphere is changing in a particular way. And this can produce these plateaus in the radiocarbon calibration. So essentially, anything that you map to this age back in the past, if you have something that is between, for example, 800 and 400 years in the past, you can't get more resolution than that because of the way the radiocarbon is changing in the atmosphere. The object could be 800 years in the past, years old, and the radiocarbon was just higher in the atmosphere at that time, or it could be 400 years old, but the radiocarbon was lower in the atmosphere at that time. And we can't separate out the two ideas. So we just have to quote an age range of 400 years, and you can't get more resolution than that. And that is very damaging in particular regions. And we call these plateaus, radiocarbon plateaus. One of them that is very, very famous, and you'll know a lot about this, is the Hallstatt plateau, which is in the first millennium BC. And it was described as a radiocarbon disaster.
Yeah, so I mean, look, so it's not in different regions. So because this is worldwide, it's just different periods of time where we have this lower resolution, and this really friggin' matters. So like I study ancient Greece, right? And you know, if you're thinking about say ancient Athens in 800 BC, it is a tiny little insignificant village, and we mostly just have graves, right? That's basically what we have. We have a little more than that. I study stuff from there, but a lot of what we have is graves from there and a few houses and things like that. But when you think about Athens in 400 BC, it is ruling a major empire across the Mediterranean. It just defeated the Persians. We have the Parthenon and major temples and all this kind of stuff. And it's like, man, if we want to understand what's going on in this period, we can't use a single radiocarbon date to understand the development of Greek city-states, to understand this flourishing that's going on in the Iron Age in the Near East at that time, what's going on with the Persian Empire, what's going on with different cultures across Europe, across North America, across China and Asia. Anywhere you go, you have this 400-year period, which you cannot do radiocarbon, at least with a single sample, to get good dates from. So let's think about what we can do. So first off, the stuff we talked about before, it's never disappeared. We still need to use traditional archaeological methods to be able to deal with the huge quantity of archaeological evidence we have. And we still can have reliable relative chronologies to help us then put things in order, in a sequence of orders, that since we have a start date and an end date of 800 and 400 BC, and we, in some places we have, you know, writing and things like that are developing and coinages right at that time, so we can start locking in some of this, and we still use the traditional relative chronologies to help us get at and have an understanding of absolute chronologies. And as I said, once we get further into the historical period, some of the traditional chronologies are far more accurate, or precise rather, than radiocarbon anyway. But how do we start picking away at this Hallstatt plateau, or these plateaus in different areas? And this article just came out. Some colleagues of mine are on it, and so this just came out really this year, and it's about understanding early Iron Age chronology. So right at this period, 800 to 600-ish BC, in the Greek world and the Mediterranean world. And so what you can do is you can start combining radiocarbon chronologies with other methods. And so, a really good one is you should start combining it with our understanding of stratigraphy and with stylistic seriation, so we can understand this sample we're taking from this layer, it most likely dates before this one from that layer, and so on and so forth. And so you can then start, once you have a large number of samples, you can start doing a type of statistical analysis known as Bayesian age modeling. And that's really valuable. That helps us start picking away at these kind of plateaus. And it's also really important because in the past people relied on one date. Now we rely on dozens, if not hundreds of dates from a site, all locked in from their stratigraphy and from the stylistic seriation that we understand of these artifacts, and then use these kind of age modelings from the radiocarbon dates we get to be able to make things more precise. Because in the end, radiocarbon dates, individual dates, are not always perfect. So carbon can be pushed down due to tree roots and moved around due to burrowing. At the same time, we mentioned that trees, if you take a date on the inner ring versus the outer ring, if it's a long-lived tree species, you might be off by 100+ years, maybe several hundred years. And so, you don't always know which part of the tree you're taking that radiocarbon date from. If it's a piece of wood that humans worked, you don't have the full trunk. And so now we don't usually use wood as often for locking in chronologies. We use short-lived organisms. So, crop species that grow once a year, or animals that only live for 4 or 5 years at a time. And so that's oftentimes what we're using to get radiocarbon dates for a site. And so that's why we have some of these arguments back and forth sometimes. A really famous one is the pyramids at Giza. A lot of pyramids are used to lock in radiocarbon chronologies, but there's some weird issues. If you look at this fit here, in this sort of hashed mark is where the historical chronology is. The black lines are the radiocarbon chronologies from different samples. And you see a lot of them overlap, but there's a large clustering of them here at Giza that date a few hundred years earlier. And so I'm not sure how the latest calibration curves have maybe updated this argument, so I don't really know, and I could be wrong here. But the argument that existed in publications until fairly recently was that perhaps the Egyptians were using old wood. So they were using older wood and turning it into the plaster and putting it in the pyramids. And so when this team and the Bonyani and others published hundreds and hundreds of radiocarbon dates, I think it was like 500 of them from Giza, they mostly lined up pretty well, but some of them were off by a few hundred years, and the explanation at the time at least was probably old wood. They were using wood that was chopped down from earlier, and in some cases there's this cedar plank that is well known. Cedar is a really, really long-lived tree. So we don't know where that piece of wood came from within the tree trunk. And so a really plausible explanation is it comes from the interior of the trunk. Right. And so that's from early on in that tree's life. And so that's why that one specific sample dates earlier. Now, I want to be clear, none of this dates as early as, say, the ancient aliens or other people think that the pyramids were built thousands of years earlier. No, this would just argue maybe that the wood is from a few hundred years earlier. And like I said, I don't know how more recent calibration models have updated this pattern or not.
So just to make this really clear for people, the carbon-14 modeling essentially assumes that you're modeling back to when the organism died. That's when the clock starts. That's when it stops taking in carbon from the atmosphere, and the carbon-14 within that organism starts to decay. However, if somebody chopped down a tree 500 years ago, got the wood from it, used it for something, and then that wood gets repurposed in the pyramid or used for a trackway or something later on, you've got a gap of 500 years where you could be off because you don't know where you started the clock. You're assuming that the wood was used as soon as it was cut down and the clock started on the carbon-14, but that might not be the case at an archaeological site. If the wood
can be reused.
Exactly.
Wood can be reused just as other things can be. And then at the same time, I want to be clear, it's not when the organism died, it's when that tissue is formed. Yeah. That's really important because that's what I'm saying about the inner part of the tree ring. It is going to have a different date from the exterior. And so the very last layer, that dates to when that tree died. But
in terms of tree rings,
but and same thing with teeth and bones of animals. So if you find a 100-year-old man and you date the bones versus the teeth, they're going to be off by about 100 years. And so because it's about when that tissue is actually laid down and formed. So
It's
yeah,
when that tissue stops being in equilibrium with the environment, when it's laid down and locked off, essentially, when it stops taking in new carbon from the environment.
And when it stops being remodeled is another way to put it. But yeah,
exactly. That's
which is
right.
going to be different for different tissues in your body, even as I'm trying to say with teeth versus bone.
That's right.
So yeah, it's going to have that complicated factor. So there's some other problems as well. Do you want to go into the reservoir effect?
Yeah. So there's a lot of reservoir effects. So what carbon-14 dating essentially assumes is that the organism is in equilibrium with its environment. So it's taking in carbon-12 and carbon-14 at the concentrations that are in the atmosphere while it's alive and while it's laying down tissue. But that might not be exactly the case. So particularly for something living in the water, for example, the carbon-14 that's being produced in the atmosphere has to dissolve in the water. And something living on the surface of the water is not only swimming in the carbon-14 levels that are coming immediately down from the atmosphere, but there's also water being recirculated from the deep ocean, and that can take up to 1,000 years. And that 1,000-year-old water, which is upwelling 1,000 years later, contains carbon-14, but it's been decaying for 1,000 years. So it has a lower level of carbon-14 that then washes up, is taken up by the turtle, for example, on the surface of the ocean. And now that turtle, if we radiocarbon date it, seems much older because it's swimming around in 1,000-year-old water that has come up from the depths of the ocean. So there's a very kind of famous example in radiocarbon dating that if you just try to radiocarbon date a dead turtle that died yesterday, you might get that it's 400 years old if you use the calibration curves for the land and assume that it's taking in the carbon-14 from the atmosphere, which it's not. You have to take into account these reservoir effects because there's a lot of carbon in the deep ocean. It takes a lot of time to recirculate. There's other effects around the world. So, for example, if you do radiocarbon measurements near a big city, fossil fuels are being burnt in that city. So imagine that you take a radiocarbon measurement of a dead pigeon in the middle of an industrial estate in a major city. That pigeon has been taking in fossil fuel carbon from the burning of fossil fuels at the local power station. So it's been washed with ancient carbon, essentially. This fossil fuel carbon was laid down millions of years ago. It's essentially completely depleted in carbon-14. It's taking in a little bit of carbon-14 that's been produced from the atmosphere, but it's also being washed with this ancient carbon. So if you try and radiocarbon date near a major urban center where there's a lot of fossil fuel fumes, you can also be off by 40, 50 years as well. So
And
there's lots and lots of these.
Yeah, so that would be, so I mean, we'll get to this, I think, but you can't really do radiocarbon dating after 1950 for a variety of reasons, due to this pollution and due to nuclear explosions. Here we are. This is what it was. So yeah, with the sort of nuclear age and nuclear testing, you can go into this if you want. We've completely adapted the atmosphere.
Yeah, so it's really, really interesting, actually. So there is, as you say, dependence on age. So you can't really go back more than 60,000 years. Why? Because the half-life of radiocarbon is about 6,000 years. So that's 10 half-lives. So you've got 10 to the 2 to the power of 10. There's hardly any radiocarbon left nowadays to do any measurements. So you can't go back than about 60,000 years. There's also a problem after 1950, as you say. So there was a hell of a lot of atomic testing that was going on in the 1950s. I think it was between the 1950s until it was stopped in 1965. And this threw a hell of a lot of radiocarbon up into the atmosphere. So you can see from this plot, I think it starts at, does it start at 1960?
50, I think, yeah.
1950. You can see the massive rise in radiocarbon after 1950. So this essentially reset the clock. It absolutely dwarfs anything that is being produced in the atmosphere by the cosmic rays. So this essentially resets the clock after 1950. However, there are some useful things you can do with this, because if you know that the levels of carbon 14 in the atmosphere are, and they're mapped very, very well after 1950, you can do things like identify victims of the Korean War. You can also expose art forgeries and bogus wines and whiskies that are supposedly vintage by checking the amount of carbon-14 in them. And if you find that they have these very, very high levels, they can't possibly be a vintage bottle of wine from, Louis XIV cellar or whatever it might be. So there's been some very useful uses of this, what they call the bomb peak in carbon-14. But in terms of it lining up with ancient times, it's very, very difficult to do that afterwards. So you have to kind of reset the clock after 1950.
So a few interesting points on that is, one, I think people are starting to work out how to do radiocarbon for after 1950, but the problem is that it can overlap with periods in time much earlier, which creates issues. Second of all, Dan Fallou's in the audience. Dan, I'm going to show an image from our article actually in a second. But he mentioned that land snails have a huge reservoir effect called the old limestone effect, because they literally eat limestone and it throws off the ratio.
Exactly. So they take up carbonate, which has ancient carbon. They take it up as shells, right? They take it up into their body. So if you do a radiocarbon measurement on that, it's like, what? Why has it got this ancient carbon within this sample? It makes no sense, because they've aggregated that into a shell. So usually when they do these measurements, what they have to do is they use a humic acid wash. So the acid wash will get rid of that carbonate. So you have to be very, very careful about the type of material that you're testing, because there are some materials that are taking up ancient carbon. So if you test a shell of a snail that just died, it will tell you that it's very, 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 very old. So you have to be very, very careful with the material that you test. With bone, you might scrape out the collagen, for example, inside. You need to be very careful about the material that you're testing, particularly around carbonate. So that's a very, very good point to make.
Yeah, for sure. So another point in the audience is they suggest you join Blue Sky with the other scientists. Since somebody asked me a question and I responded that I already talked to Mr. Beat about it on Blue Sky. And then one last funny point about this, which I always like to point out to students, is because of this nuclear testing and because of the development of radiocarbon dating starting with Willard Libby in 1950, that is considered present. So for all scientific analysis going back to before present, when you see BP dates before present, you might think, well, if the article was published in 1970, well, 1970 is present for them. And if it's published in 2024, well, then 2024 is present for that. No. 1950 is the present, and we are living in the future. We are at 74 AP after present. And I think that that's how we can solve all of our religious chronologies and deal with that, because I had a good meme on that. Damn, I didn't throw it in. But that's okay. Yeah,
I feel like it should be whatever what was the central junction of the universe in terms of time in Back to the Future? Was it 1985 or something?
Something like that, yeah.
Yeah, I feel like it would be better if it was 98, but essentially we have the same situation here where you set a standard date and you go backwards from that, and all the calibration curves do that. The interesting thing as well is they also all use a wrong half-life for carbon-14, because there were different half-lives used over different periods as the half-life was measured more accurately. So they all use this pretty wrong carbon-14 half-life, but they do the correction for the correct half-life, so it doesn't matter. But you have to have these standards so that you can compare, as you say, measurements that were made in different periods, because you need to know how long you're going back, and also you need to know what carbon half-life you were using when those measurements were made.
Exactly, that's a good point. Yeah, especially as archaeology keeps going and we keep, in 300 years, it's going to be a different set of stuff. Yeah. So another limitation is we need organic material. So we need actually organic material that preserves this. So in bone, for example, that's collagen usually. In certain contexts, in waterlogged contexts, anaerobic contexts, in glaciers, for example, this is from Ötzi, the Iceman on the right, we'll get other kinds of more fragile plant materials. We might get carbonized seeds, but these only come up occasionally, and in some environments you don't get very good organic preservation. For example, I mentioned Dan Fallou, who's in the audience, friend of the channel. We published a paper together looking at the really poor preservation of organic materials at this site in Greece called Nicoria, and it just has to do with the soil conditions. And it always has to do with depositional environment. Some people have this mistaken idea that stuff just decays at a known rate. No, the older things can preserve depending on where they're deposited and how. And so, waterlogged environments, anaerobic environments, they're very good for preserving organic materials. And that's really good, therefore, for getting radiocarbon dates, unless it's in the ocean where you might have that reservoir effect, of course.
There's another important point to make just while you're talking about the nature of the site as well. And you kind of flagged it up with a really nice picture earlier. If you have roots that are going down into these sites as well, you're contaminating this ancient laid down material with modern organic material. So these roots are coming down and they're exchanging carbon in that material. So when you make these measurements, not only do you have to wash off carbonate, for example, but if you've got any little rootlets that are on there, those need to be removed as a matter of course. And you need to remove any potentially contaminating modern organic material. So like you said, things on the surface very, very difficult to use because they're getting covered in organic material from the modern day. So but this also happens under the ground. If you have root systems which are growing into these sites, you have to be very, very careful.
Yeah, exactly. And so we do a lot of different procedures in the labs, like when we extract collagen to make sure we're getting the collagen from that organism. We demineralize everything after cleaning it and all this kind of stuff. Yeah, and then there's also new methods that are done. This is actually really useful when there is poor preservation or when you're trying to use short-lived species. So in the past, we'd do bulk radiocarbon from like large hunks of wood. Now we have what's called accelerated mass spectrometry, and we can use much smaller samples. Do you want to walk everybody through how a mass spectrometer works?
Yeah, for sure. So there's basically two ways that you can measure the amount of radiocarbon that's in your sample today. So one way is to use the decay of the material. So the carbon-14 is decaying. It's doing that decay that we showed earlier, which is carbon to nitrogen, and it emits electrons. And you can capture these electrons coming out. Usually you add a scintillator to the material, and you get flashes of light as these electrons go through the scintillator. This was an older way of doing things. And there, essentially, you're measuring how many of the carbon-14 atoms are decaying over time. And because the amount of decays is related to the number of carbon-14 atoms in the sample, you can measure the amount of carbon-14 atoms in the sample. However, that's very, 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 very slow because the half-life is 6,000 years. So you have to sit there for ages counting flashes of light. And that also limits your accuracy because you're seeing very, very few of these pinks, right? So you have a kind of small data set. Nowadays, we use what we call accelerated mass spectrometry. So what you can do is essentially vaporize a sample with this carbon inside it. You can bombard it with ions to create essentially carbon ions, or ions containing radioactive carbon. And these ions will contain either carbon-12, carbon-13, or carbon-14. You accelerate them in a magnetic field and an electric field, and you bend them. And the different masses, carbon-12, carbon-13, carbon-14, they will bend at slightly different rates because they have slightly different masses. And you can actually count the number of atoms of carbon-12, carbon-13, and carbon-14 in a sample. So here you're directly measuring the number of those atoms in the sample rather than watching the small number that decay. And that's brilliant because it means you can get the answers much more quickly, because you're not just waiting for these flashes of light. And also you can use far, far smaller samples because instead of looking at the tiny number that are decaying, you're looking at the whole sample. So you can use a sample which is 1,000 times smaller. So you can use kind of micrograms of a sample. So if you have a very, very small sample that's preserved, you can get a measurement with AMS. Or if you have a beautiful painting that people don't want to be scraping huge hunks off to do a measurement, you can do it with a tiny paint fleck with AMS. So very, very useful for using smaller samples and also for getting answers much more quickly. The problem with it, of course, is that you need an accelerator and you need a mass spectrometer. So it can be a little bit more expensive to set up. And it needs these modern pieces of kit. But otherwise, you can use much smaller samples and much, much quicker. So it really has revolutionized the field.
And I mean, as I mentioned before, I do different carbon isotopes. I actually measure carbon-13 and carbon-12. So these kind of mass spectrometers are becoming an essential kit towards understanding archaeology in a wide variety of ways. Understanding ratios of strontium isotopes tells us about the geology where an organism lived back in the past. And so, you know, we can get trade therefore, and so, or migration. And so, yeah, so there's a lot more that these mass spectrometers that calculate the weight of these different isotopes and then put together those ratios. There's a lot we can say from them, and so they're very, very valuable. So I wanted to end by giving a little recent teaching example of something I actually just taught Monday in a class here at Cardiff. And I'll put you on the spot, Sam, to see what you can come up with. So this is an excavation that's really interesting. This was dug by General Pitt Rivers back in the late 19th century, the site of Warbarrow in the UK. And it was this tomb. So just a quick warning, I'm going to show some human remains here. So it was dug in the 19th century, no good chronologies for it, right? Because it was from that period. And so some scholars said, hey, let's start thinking about dating this and understanding it. And we need to select radiocarbon samples. And we want to understand not just the absolute date, but what's going on relatively there, relative chronologies. How can we put together multiple lines of evidence to start getting more precise, right? So what they did was they had many, many photographs from this excavation in the 19th century that showed this kind of burial here in this rectangular space. And there was a number of different skeletons mingled together, as you can see from this photo. And then not all the bones were preserved for study, but a number of them were. And so they worked very meticulously to put together this kind of drawing, and using the bones that were present and matching them to those photographs from the 19th century. And this is how they could say, hey, these were the different individuals there. The bones we couldn't identify as belonging to an individual, that's this big blue blob. We just can't tell where they go. So what do you see here? How many burials do you see here, Sam?
I mean, you've got the light blue, the kind of turquoise, you've got the yellow. I mean, so you've got at least 3, and then they've got the kind of assorted jumble. So I'm going to go for 4. I'm going to go for 4.
4 what? 4 skeletons here.
4
yeah,
skeletons.
Well, so there's actually 6 for sure. That's these different phases here, but not different phases, different numbers here. So there's this one, there's the orange one, there's these 2 represented by skulls, and this one represented by skulls and some bones. Now, can you put together the order of burial here?
Ooh. Can I put together the order of burial? Well, it looks like the 2 on the right were laid down. It looks like they were very carefully put down, doesn't it? It looks like they were. So,
and notice that they're in alignment with the actual tomb itself.
Yeah, so I'm going to go with the light blue and the turquoise were put in there first, because it looks like they were designed to be there.
You'd ace my class. Good.
Okay, good. It looks like the other ones were kind of thrown on top.
To a certain degree, yeah. So what they argued was that, you notice how the upper half, the torso of 1 and 2 are still good, while the lower legs are weirdly positioned? So probably these 2 were laid out fully prone, so extended out across the entire tomb. They wanted to reuse the tomb, so they carefully moved the legs and pushed them up towards the torso. And then they laid in probably the orange one and the green one. Right. And then last on top of those, they noticed they mixed up the leg bones again of the orange one, and then they laid in the yellow one and the purple one, and everything was just a jumble there in that corner. And so they actually took that and did radiocarbon dating on each of these individuals, and the radiocarbon dating lined up perfectly for that kind of chronology. And so we can see the phasing of this crypt in a sense, where it starts off as 2 burials side by side at the lower left here. Then they scrunch up the legs there and they put in 2 new burials, but sort of crouched. And then they throw in the next 2, potentially one after another. It's unclear. They think it's one after another because of these radiocarbon dates showing up. There was more radiocarbon in one over another.
So radiocarbon kind of tells that story where you can kind of, if you squint your eyes, you can kind of see that that's what might have happened, but you can confirm that with the the radiocarbon dates. That's amazing.
And so, first of all, thank everybody for the super chats. Yeah, exactly. I think that that's what's so cool, and that's, I think, the lesson here is kind of like the importance of taking all these different ways and methods and disciplines and combining them together as independent lines of evidence that can check one another to be able to understand, you know, in this case, the archaeological record. And I guess I actually did have something else to end on about it not being just for archaeology. We've been talking about how this has also helped us put together our understanding of the Earth system. Right? This the Earth system in the past, to be able to understand change over time. And so like the atmosphere in different places. And so it helped us test, you know, the end of the Ice Age and the development of the Ice Age and the chronology for it. And it also helped us start to prove global warming was human caused. Do you want to go into that a little?
Yeah, I can go into that a little bit. So the carbon that has been put into the atmosphere now. So we know carbon dioxide in the atmosphere is rising. But people could say, well, is that really coming from fossil fuels? Is that really coming from human activity? Well, if the carbon is coming from burning of fossil fuels, those fossil fuels are from organic material that died millions and millions of years ago. So you would expect that it contains no carbon-14. And what we see nowadays is that if we test the carbon dioxide that is in the atmosphere, we see it's completely depleted of carbon-14. So the ratio between carbon-12 and carbon-14 is changing. There's more carbon-12 in the atmosphere compared to carbon-14. This is called the Zeus effect, I believe. So we can actually map and measure the amount of carbon, ancient carbon, that we're pumping into the atmosphere. And we know, or at least it's consistent with the idea that we're pumping lots and lots and lots of ancient carbon into the atmosphere. This is not carbon that's being produced by more cosmic ray activity, for example, because then we would have more carbon-14. So this helps to prove that humans are behind man-made climate change. So this is a huge impact of carbon-14.
We have completely altered the atmosphere. And so, yeah, I think that's kind of the end. I mean, you know, so, I mean, we should take some questions from the audience, I think. But I think the key point here, the key takeaway is this is just, it really highlights this interdisciplinarity between physics and archaeology, environmental sciences. And at the same time, I want to emphasize that traditional methods are not out of date. Radiocarbon costs money, and archaeology projects are poor. So we do still rely on ceramic chronologies when we can, but we're constantly testing them with selected samples, just like that team carefully selected the samples from those skeletons in order to understand stuff. We carefully select samples from different stratigraphic profiles and whatnot. So yeah, anything else you want to end on before we take some questions?
I wanted to tell you my favorite example here in archaeology. So there was a beautiful paper. I think I sent it through to you. You might have it, you might not. But where carbon-14 helped to establish the overlap between the modern calendar that we use and the ancient Mayan calendar in Central America. So they did carbon-14 measurements on a wooden lintel collected from Tikal, bearing Mayan calendar dates. And then obviously you have the Mayan calendar date, you have the date from the carbon-14, and you can overlap the Mayan calendar dates with the modern dates. This is one of the massive impacts that carbon-14 can have to help us overlay the calendars between modern civilization and an ancient civilization. I thought that was an absolutely amazing application of this. There was also an application where it was used to show the ancestry in Australia and show that the Australian Aboriginal people arrived there about 50,000 years ago. So it helped to kind of ease that political tension there and show that these people were there on the land before. So lots and lots of applications of this useful in kind of science, archaeology, politics, climate change. It's everywhere. Carbon-14 is in all of these applications, and it really is the most amazing field.
Yeah, and I mean, it really did revolutionize all of archaeology. I mean, I just want to make that clear. Like every single bit of chronology, basically going back 50,000 years, has been impacted by radiocarbon, and so it's kind of cool to see the field update and change. And that just brings back one last point I want to end on with archaeology itself: is it's not new discoveries that revolutionize the field; it's new methods. You know, so I mentioned there's the second Nobel Prize related to archaeology was the development of sequencing the Neanderthal genome by Svante Pääbo. And so it's these new methods, doing ancient DNA, doing isotope analysis, doing radiocarbon, applying geological sciences, environmental sciences, different disciplines to the field, that is what revolutionizes our understanding and really causes paradigm shifts. Very few discoveries, especially in the last 100 years, I can't think of any, have completely revolutionized everything. It's new methods that completely revolutionize everything. And so the public gets this wrong sometimes when they highlight Göbekli Tepe. And it's like, no, Göbekli Tepe is fucking cool. Don't get me wrong. But it did not change all of our understanding of all of human prehistory, regardless of all the YouTube channels that say it did. It really did not. It was radiocarbon that did. It's ancient DNA that did. It's all these other fields that did. And so, you know, that's, I think, something that people should take away from this.
It's really interesting that you have this. So it's not necessarily Indiana Jones finding a new tomb which is under Antarctica and driving the field forward. It's actually the findings that we already have and finding new ways to interrogate those samples that we already have. There's so much more information in those samples when we come up with these new methods. We can revisit them and we can learn more, which is really, really fascinating because we have so many materials that we can. And this is important. We talked about this before with the lead from ancient ships. It's really important to preserve these samples because later on down the line, new analysis techniques will come online, and we need those samples still to be well preserved and in their original conditions, so that we can do that later analysis.
Yeah, I completely agree. And this is part of what archaeology needs desperate funding for, is for preservation and curation for future people to study stuff. We gave some examples there. So, okay, so we have a few questions. History Dose asks, what are the methods used to date petroglyphs and footprints? History Dose, we're going to save that for a later collaboration video where we talk about some other dating methods that come from physics as well. Sorry not to answer you, but they vary based on the context is the real answer there. Why is carbon dating so expensive? Because it requires setting up these kind of labs. Is really what these days it requires a mass spectrometer. AMS is far more accurate and it's far more effective and it destroys far less material. So we just need to set up more labs and make the material cheaper to set up high quality scientific labs. To be honest, public funding for sciences and education is how we make this cheaper, to be able to build that infrastructure.
Particle accelerators are expensive, which is a major bugbear in my field at the moment. When we want 22 billion for the next one, this is we don't quite need one that big for the old the carbon-14 dating. But look, you need specialized equipment. You need people in the lab who know how to prepare these samples, how to make sure they're not contaminated, who work long hours. They know what they're doing. So you need to pay qualified people, and you need to set up labs with specialist equipment, and that costs money.
Yeah, it costs a lot of money, and yeah, the experts are in many ways the most expensive thing because you have to pay people, and we should be paid a living wage to do this kind of stuff, which these days many of us are not. Let's just leave it on that. Somebody asked if we could use the amount of microplastic found in bones to date present humans in the future. Maybe. I don't know if you get microplastic per se, but maybe you'd find chemical signatures. I'm not sure if that
there was a really good meme I saw about that, actually, Flint. They were talking about, obviously you have these paleo people who they say they're eating, you know, like ancient humans. They only eat meat and these kind of things. And they said 50,000 years in the future, those people are going to dig up our remains and they're going to say that, oh, the paleo people, they ate lots of microplastics, so I'm just going to eat microplastics and I will be healthier than anyone in this amazing new future. So we are going to be the paleo diet of the future, and it's going to be tons and tons of little pellets of plastic, apparently. So
yeah, exactly. History Dose asked you what your favorite discoveries were using carbon dating, but you actually answered that, so I think he asked it right before you did it.
Yeah.
or she. I'm not sure. Can you give an example of archaeological chronology being really revised due to C14? JB, if you weren't here earlier on, I talked about the revision of megalithic tombs in
diffusion,
Europe changing by thousands of years, where people thought that they diffused from southeast Mediterranean to Britain and France, and now we actually understand that the chronologies are completely off by thousands of years. The end of the Ice Age was something that changed by 10,000 years, I think, or so. A lot of things changed by thousands, if not tens of thousands of years, and others just by hundreds even, but that matters at times.
And you still get from time to time kind of carbon-14 measurements popping up in the press, right? I'm sure the Turin shroud's been redated, 100
I think I
times
saw
or
people
whatever it
chatting
might
about
be.
that, yeah.
Yeah.
Yeah. How much current carbon pollution actually affects the results of C14 tests for dating archaeological artifacts? So I guess they're talking about contamination.
I had some numbers here if I can find, because I had a look at this. So yes, I don't think I have how much it changes it, unfortunately, quantitatively, but it does change it because you're pumping a lot of old C14 depleted carbon into the atmosphere, which the organic material is absorbing, excuse me. So obviously material from the early 20th century onwards, where there's lots and lots of this ancient carbon in the atmosphere now, appears older. And you actually get a similar effect, like I said, around large cities and also volcanoes, which are pumping out a lot of this ancient carbon as well. So you have to do these corrections around large cities and around volcanoes. I can't give you, unfortunately, any solid numbers, but I believe we're talking about potentially tens of years, so decades, if you don't take this into account. That's what I remember reading, and hopefully someone will correct me if that's not right. But I think we're talking about decades here if you don't correct for these effects.
And also, just to make a point, if you're talking about stuff that's already buried, so does modern pollution impact the radiocarbon age of bone from 10,000 years ago? The answer is usually not. As long as you're selecting it from an environment where there's not going to be some sort of contamination and diagenesis, where it's exchanging chemicals with the surrounding matrix that it's buried in, it should not have a big impact. But in certain burial contexts, that kind of diagenesis can happen. And so you would not want to select a sample where you think that kind of diagenesis is happening to begin with, and also why you'd want to take many samples across a site where there's different depositional environments and run that Bayesian statistical analysis on it. Someone said uranium, thorium for petroglyphs. Yes, depending on the context. I hope we'll do uranium, thorium at some point.
There was the interesting thing so those tree rings can go back to about 14,000 years. So how do you get to 60? They use things like I think it's speleothems, growths of coral. So there are other things apart from tree rings that grow at predictable rates. You talked about varves, things like layers of sedimentation in the ocean, the growths of coral reefs. These grow by predictable amounts each year, and you can therefore make assumptions about the age of something when you take a sample from a particular depth, maybe. So you can project back to about 60,000 years, but you have to use more assumptions about the depositional and growth rates. So it's a little bit tougher after about 14,000 years into the past, where tree rings can get you to.
Yeah, and in fact, some of this contamination, I'll try to answer two of these questions at the same time on contamination and peopling of the Americas. So I'm sure some people here in the audience are familiar with the larger debate about Clovis and pre-Clovis and the peopling of the Americas and when it happened. And I mean, pretty much these days, all archaeologists understand that it happened in the pre-Clovis, probably as far back as 20,000 plus years ago, based on the analysis from White Sands. But one of the very early pre-Clovis sites, and now I'm blanking on the name, a lot of archaeologists were skeptical of the dates, specifically the radiocarbon dates, because it was in an area where there was coal mining. And so they thought that maybe some of that coal had leached and impacted, contaminated the samples, leading to a date that seemed older than it actually was. Turns out that's not the case. The dates have been checked and checked and rechecked and rechecked, and it's fine. and they've demonstrated beyond a shadow of a doubt that site. Now I'm blanking on the damn site. I think it was the one that James Adavazio did, but it doesn't matter. But so the point is yes, the radiocarbon chronologies have had a huge impact on the peopling of the Americas, and these issues we're talking about with contamination have actually fueled a lot of the arguments with that. So it's actually something that we do go back and forth on, and it is something that's important. This is why, to be able to do archaeology and be an expert in this kind of stuff, you need to really understand these kind of different subfields, right? You need to, if you really want to start talking about the age of the peopling of the Americas, you need to understand the basics of radiocarbon and the issues of contamination and the issues of calibration. It's actually really, really important, and if you don't get that stuff, well, I don't understand how you can really argue about any of these things online, but people will do that. So yeah, so I think that can lichen dating be used regarding megaliths?
I guess that question that just came up is kind of similar to that one about the ancestral history of people in Australia as well, right? So you can get an idea of when these different groups of people were on a continent, which is very, very useful.
Yeah, yeah. Okay. I think we're running low on questions. We've been going for an hour and a half, so plenty of time. I do want to thank everybody for showing up. How many of you are here? I don't even know. I think I can see that with this.
Some really, really fantastic questions.
Yeah, really good questions, really lively conversation. I want to thank everybody. As somebody mentioned, I think at some point I crossed 40,000 subscribers. I also crossed 1 million total long video views. And so things are moving along. This channel's growing, and I want to thank everybody for the support. And obviously my colleagues that are in the audience and Sam here, because it's these collaborations that I really believe in. I'm not a guru who proposes everything as if it's my idea. I'm here to educate the consensus of what we do and how we do it, because I think that people like Sam, people like myself, we're very skilled at explaining this stuff clearly for people that are interested, and I think it's really important to get this educational information out there so that people have a better understanding of physics, archaeology, environmental sciences, and whatnot. And so, yeah, thank you, everybody. I really, really do appreciate it. And yeah, things are going well. I just bought a new computer yesterday, so my live streaming abilities should increase. Maybe we could start having conversations with a few people. Let's see how that goes with it. I have to borrow my wife's computer whenever I live stream, and so I'm hoping.
Just waiting outside the room now. Come on, Flip.
Well, yeah, so she sometimes listens in and gives me some info. But and we have a fun video dropping, I think, tomorrow night on the Oracle of Delphi and whether she was stoned out of her mind. So we're going to delve into the history, into the science, and it is one of our best produced videos. It looks and sounds, and we have custom music made by Bettina Joy de Guzman. She's a lyre player and a classicist. Wow. And we have some really cool animations and some voice acting, a little bit done by Dan Fallu, who was in the audience. So everybody stay tuned for that. Was she stoned? You'll soon know.
I'm so glad, honestly, Flint, I'm so happy to see how well things are going. It's fantastic, because the messages that you're putting out there about scientific rigor, sticking to the truth, not just standing on a pulpit and telling people how it's going to be. I think these are absolutely amazing messages that people want to hear, need to hear. And it's amazing that so many people are here listening to them. And listening to what you're saying and asking such amazing questions, because that's the other half of it. Absolutely brilliant. And I couldn't be more happy for your success. So long may it continue. The last time, I think when you came on my channel, I was the one at like 30, you were at like 10, and now we've swapped. So it's absolutely amazing. So I'm so happy to see. And yeah, keep it up, and everyone in the audience, keep asking your awesome questions, because that's how we all learn together.
And everybody go subscribe to Sam right now. And we're gonna we've been talking about putting together. We just did the Real Archaeology Festival last month, and I know all the archaeology YouTubers want to do another one of those. But we're also starting to talk about maybe organizing a Scholars of YouTube festival, where those of us that are practicing scholars and educators, we put together a nice festival of videos. So I hope that we can build this ecosystem. It's not about one or the other. We want us all to succeed, because we really want to get out good science and good scholarship and good education and good information in an interesting, accessible way.
There's no time where it's been more required than, well, I shouldn't say that, but it's very much required at the current time. Flint, but just before we finish off, obviously we've discussed carbon-14 dating to date. It can be slightly intricate, it can be slightly difficult to take in on the first go. I think you're interested in doing a kind of deep dive video on it as well. I'd love to be involved with that if that's something you want to do as well, and maybe we can get that out to people as well. So if people want to sit and go through it in the gory details as well, we can help them with that down the line.
Well, and this is replayable, but yes, at some point I want to do like a documentary type thing on radiocarbon and the revolution and stuff like that. But that's like a big job, and it's low on the list right this second. But it is there because I think it's important to put it in a way that's extremely accessible and digestible. But yes, this live stream, go share it with people. It'll be accessible. A lot of my live streams, I think most of the views come afterwards anyway. So I expect people will be listening in. And if you're one of those people, leave a comment, say hi to Sam, and maybe everybody leave a comment about what physics topic you'd like the two of us to collaborate on next. And yeah, thank you. Like, share, subscribe to both of us, and get the word out. Good science. Peace out, y'all.
Take care.